The second law of thermodynamics says this thing called entropy is always increasing in the universe. Entropy is often described as disorder or chaos or randomness. I'll introduce a few other terms to help us imagine what entropy is. Here's another example of how order increases locally but at the expense of creating disorder elsewhere. This is a hydroelectric dam. The water in the lake has potential energy. The potential energy of this water will be transduced to electrical energy as it flows through the dam, but with increased entropy. That is, the water will experience an increased disorderly random motion as it flows through the dam, so that down in the stream bed the water will be in much greater motion than it was at the top of the dam. The water at the bottom of the dam, I think we would all agree, is less potentially useful than the water above the dam. Another way to look at this is to say that the water in the stream bed below the dam is more useless, or by comparison to the potentially useful water in the lake, the water that has already flowed through the dam is now useless. So entropy then can be seen as useless energy, energy that can't be used to do anything productive, unlike the water in the lake. Well, if entropy, or this disorderliness or randomness, is in fact useless energy, then all kinds of energy can be grouped into just two kinds: useless and its opposite, useful. So here I've drawn the universe again, and I've simply said that all kinds of energy that I had in the previous universe are useful kinds, and there's a certain amount of randomness or entropy already in the universe, so I've populated the universe with some useless energy as well. When I animate this picture, you will see events that are consistent with the first law of thermodynamics, but that also obey the second law. And there they are. Useless energy has increased at the expense of useful energy, and this is indeed consistent with the first law, because you'll see that neither useful nor useless energy has left the universe nor come into the universe. And though it's not stated on the slide, it is not only consistent with the first law but also with the second law saying that universal entropy always increases. Well, we had an equation I showed you a moment ago, and the goal of this discussion is, at least in part, to understand where this equation comes from. So let's start making some arithmetic statements of the first law. Let's try and put into math language what the first law says, and then we'll do the same thing to accommodate the second law. So the first thing is a very simple equation. It just says that total universal energy is equal to the sum of all the kinds of energy in the universe at any given moment. You can add some of the other kinds of energy that are not on this list. Or, to make it very simple, the total amount of energy in the universe is simply the sum of all of the energy that is useful and all of the energy that is entropic or useless in the universe at any given moment. Let me say a word or two about universal energy and its constancy. To say it is constant means that the change in universal energy over time has got to equal zero. So this is another mathematical statement or construct that says the first law. It says that the change in universal energy is equal to zero. In other words, universal energy does not change. It's neither created nor is it destroyed. The Greek letter delta, as you probably know, just means change in. So when you see it in front of some term, it means change in that term. Well, we can also say then that the sum of the change in useful energy and the change in useless energy must also equal zero. That comes from the second equation near the top of this slide. If we do that, then we can solve for the change in useful energy. And that's shown in green right here. The change in useful energy is equal to minus the change in useless energy. This statement conforms to both the first and the second law of thermodynamics. And what is interesting about it is that it establishes or states a reciprocal relationship between the two quantities. Graphed this way, useful energy is always declining, and useless energy is always increasing reciprocally. I've introduced two terms here, stability and instability, which I haven't spoken of yet. So to give you an idea of what I mean, if entropy, which is rising, means disorder is rising, it also means that there is an increase in the stability of the universe. Imagine I have in my hand a bunch of paper clips all scrunched together in my fist, and I hold my fist over the instructor's table in class. When I let go, of course, the paper clips are not going to stay suspended in air. They're going to drop due to the force of gravity, and as they drop, they're going to spread out, and when they hit the counter, they'll spread out some more. So the paper clips, in dropping from a height, have experienced an increase in disorder, an increase in entropy. They did this because being on the table is a more stable state than being up in the air, unless I'm holding them, of course. And that's the concept of entropy as being stable, or more stable than useful energy. Another way of saying this is that everything that happens in the world, every event, happens because something about the components or participants in the event is unstable, and spontaneously the components attempt to achieve some level of stability. So entropy is really the driving force in the universe. The second law is the driving force in the universe. It says entropy is always increasing in the universe, but what it really is saying is entropy will always increase in the universe, and as a result, things will happen.